Assalamualaikum everyone. We are Group 4 and today we will be presenting about the reverse Shamir-Edelman algorithm, or more commonly known as RSA. It is one of the most widely used encryption methods in cybersecurity. This presentation is prepared by three of us in the group: Mas Damia, myself, Nurul Fatiha, and Nur Najwa Shohada. Each of us will be explaining different sections of the project, including theory, applications, and implementations.
I am Najwa. I will start with the definition. The RSA algorithm, reverse Shamir-Edelman, is a common public key cryptography method that facilitates safe data transmission. It was created on the 1977 by Ron Rivers, Adi Shamir, and Leonard Edelman, using two keys, which is a public key for encryption, a private key for decryption. RSA is an asymmetric encryption method. It depends on the mathematical challenge of factoring the product of two huge prime integers. Why we do need cryptography? First, it helps protect data when we send it over the internet, whether for online shopping, sending private message, or logging into account. Without it, our personal and financial information could be exposed. Next, there are two main cryptography, which is symmetric key, where the same key is used for both encryption and decryption. And the second one is asymmetric key, also called as a public key cryptography, which use two keys, a public key to encrypt and a private key to decrypt it. This public-private system is more secure and is also allow digital signature, which help verify the identity of the sender. Now, let's talk about RSA, one of the most popular asymmetric algorithm. RSA works encrypting plain text into cheaper text using the public key and decrypting it back using the private key. RSA is widely used today in web browser, email, mobile apps, VPN, and secure communication platform. To conclude, RSA is safe, trusted, and essential method that help keep our online activity secure. Let's move on real-life application of RSA. Let's begin with the first one, which is web security. When we visit a security, you may notice a padlock symbol in the browser. This indicates the use of HTTPS, which is rely on RSA to protect the data we send and receive, like password, credit card detail. RSA help encrypt the decision key during handshake process, making the web communication secure. So the second one is digital signature. It verifies identity of sender. It ensures the message and document integrity is used in secure emails and legal documentation. So the third one is cloud storage. RSA is used to protect the data before uploading it into the cloud platform like Google Drive or Dropbox. It helps secure encryption key and manage file sharing without exposing sensitive information. Even the cloud provider cannot access it. Next, we have a secure messaging. Apps like WhatsApp and Signal use RSA for end-to-end encryption. When you send a message, it gets encrypted with the receiver public key, and only they can encrypt it. This secure complete privacy. Even the app itself cannot read the message. So the last one is online banking. It's secure transaction and OTPs. It used by PayPal, MyBank2You, CMB Click, and it's enable trusted digital banking.
Hi, I'm Fatiha. So, RSA has several advantages. It is reliable for privacy and data integrity. The content stays unchanged during transmission. Its strength comes from the difficulty of factoring large prime numbers, which makes it extremely secure, especially when using key sizes of 2048 bits or more. RSA has also been studied and tested for decades, so it is trusted and widely adopted in many secure systems today. On the downside, RSA can be slow because it is computationally heavy, especially with large key sizes. That makes it less suitable for real-time or large data processing. It also requires careful key management. A small mistake can lead to vulnerabilities, and in the future, RSA may become vulnerable to quantum computing, which could break the encryption using algorithms like SHORS That is why researchers are already working on quantum-resistant alternatives. The RSA algorithms works using large prime numbers and modular arithmetic. It starts by selecting two different prime numbers, p and q, which are multiplied to get a value called n. Then we calculate something called phi of n, which is the number of value less than n that are co-prime to it. Next, we choose a public key value, E, that is also co-prime with phi. After that, we calculate the private key, D, which is the modular inverse of E. These two values, the public and private key, are used for encryption and decryption. When a message is encrypted using the recipient's public key, it can only be decrypted with the correct private key. This ensures that even if someone intercepts the message, they cannot read it without access to the private key.
Now let's walk through the mathematical representation of the RAC algorithm using a simple example with small prime numbers. We start by choosing two prime numbers, p equal to 17 and q equal to 19. We calculate n, which is the product of p and q. Now n is equal to 323. This value of n will be used as part of both the public and private keys. Next, we calculate Euler's torsion function. The formula is p minus 1 multiplied by q minus 1, which now equal to 288. Now we choose a public exponent, e equal to 7, which is a number that is relatively prime to 288. For encryption, we will use the plain text message pt equal to 6. Before encrypting, we calculate the private key d, which is the modular inverse of e modulo phi n. We will use this formula until the answer is a whole number. Now the final answer of D is 247. So now we got the value of public and private key. For the encryption process, we use the formula Ct equal to Pt to the power of E mod n. So the Ct now is 218. To decrypt, we reverse the process using the formula Pt equal to Ct to the power of t mod n, which gives us back to the original plain text, which is 6. This confirms the encryption and decryption work correctly using RSA. So let's walk through the basic pseudocode for how RSA encryption and decryption works. We start by generating two large prime numbers, p and q. These primes are fundamental to the security of RSA. So, like previously, we compute n, which is the product of p and q. This value of n will be used as part of both the public and private keys. After that, we calculate the Euler's torsion function again, which is phi. The formula is p minus 1 multiplied by q minus 1. Now we need to select a public exponent e. This should be a number greater than 1 and less than phi, and it must be co-prime with phi. Meaning the greatest common divisor of e and phi should be 1. With e chosen, we then compute the private key d. This is the modular inverse of e mod phi, meaning d multiply e modular phi should equal to 1. We now have our key pairs. The public key consists of e and n. For encryption, we take a plain text message from user input and first convert it to a numerical format, typically a big integer. We encrypt the message using the formula C equal to m to the power of e mod n, where C is the ciphertext. To decrypt, we use the private key with the formula m equal to C to the power of t mod n to retrieve the original message. Finally, we convert the numerical result back to a readable string format and display the decrypted message. And that completes the RSA encryption and decryption cycle. Okay, so from the previous pseudocode, this is how we implement it into a Java code. The output shows the encryption of plain text into a ciphertext followed by its decryption back into the plain text.
To conclude, RSA is a widely used algorithm for secure communication. It helps ensure data confidentiality, authenticity, and integrity. In this project, we successfully implemented RSA in Java and demonstrated how encryption and decryption work. Even though RSA can be slower with large key sizes and may face risks from future quantum computing, it is still considered a reliable and trusted standard in cybersecurity today. Overall, this project has helped us better understand how encryption works and its importance in real world applications. Thank you.